Hello, and welcome back to the Maths Behind the Economics YouTube channel and the Logarithms for Economics series. This is video 13, and in this specific video, we're going to deal with the rule that tells us what to do when we have got an exponent in the base of the logarithm. As always, first we're going to discuss the rule itself, then we'll look at and prove why the rule works, and in the last section of the video, you will see plenty of examples. Let's get started. On the screen now, you can see a nice and neat version of the rule. So what does this rule tell us? The rule tells us that if we have a base that is raised to some exponent, we can rewrite that then as a log, which is the same base but without the exponent, multiplied by 1 over the exponent that was in the original base. So what would it look like in the case of the natural logarithm, which is very often used in economics? So it would look something like log e to the nx equals 1 over n ln x. So let us have a look at some examples and have a feel for whether this rule is true or not. So for example, if we had log base 5, first of all, we recognize that 4 is equal to squared. So this is the same as log 2 squared 5. That means we could apply our rule, and if the rule is true for every single base and every single argument, then this could be replaced as 1 over 2 times log base 2 5. Remember, here in the log base, we have got a exponent, and the base of that exponent is 2. So that's going to stay in the new rewritten log base. And the exponent or the power of that log base was 2, which comes out as a 1 over 2 multiplier. So let's make a bit more space and then use the calculator to convince us that these two things are indeed equal. So we know that log base 5 using the calculator is equal to 1.160964047, and I've just copied over every single digit that's my calculator displayed once I put this log into it. The next thing I want to check is what 1 over log base 5 is equal to. And using the calculator, that gives me 1.160964047. Well, I shouldn't have any surprises because, these rules have been around for thousands of years, so I shouldn't really come up with a result that the two are not equal. However, I'm trying to demonstrate you what mathematics does when mathematics is trying to come up with new ideas. So that was one example. I demonstrated it to you that it works in one example. Let's have a look at another example so we can start to build up some confidence that this should be working for every single base and argument. So for that, again, we need a bit more space. And this example will be log base 8, 9. Well, first of all, I noticed that 8 is 2 cubed. So I can rewrite this as log base 2 cubed 9. Another question is that equal to 1 over 3 log base 2 9? Again, in the original log, the base is an exponent, and the base of that exponent is 2. So in the new form of the equivalence, the base also have to be 2, but in this case it's not just a single base, not an exponent of a base. And also the power of the original base now is a multiplier outside in front of the log. So again, calling on the calculator, log base 8 9 is equal to 1.056641667, and then 1 over 3 log base 2 9 is equal to 1.056641667. Again, we shouldn't be surprised about it. Now that we have tried this rule out on a few examples, we started to build up a feeling for the rule. Now let's go down to business and properly prove it and see why this works in every single case. So again, make more space. So why does this rule work? First of all, what we need to do is lay the ground. So remember, when we talk about logs, we have to have some restrictions on the base and we have to have some restrictions on the argument. Let b be a positive number. Remember, we can't have a negative or a zero base, but on top of that, we cannot have a base that is equal to 1 If you don't remember these things, go and check out video 2 in the series. I will link it for you. On top of that, our argument, which in this case we're going to use x for, also have to be a positive number. However, there is going to be an exponent in our base, let's say an exponent of n, and because our log base cannot equal to 1, we have to make sure that the exponent, the power of that base, whatever that base was, is not going to be equal to 0, because remember again, any number raised to the 0 power is always going to be equal to 1. So for us, restricting the base not being equal to 1 is not enough, because let's say my base is 2, but if I raise 2 to the 0 power, I still accidentally end up with a base of 1, which is not allowed for the logs, because then the log concept itself wouldn't work. So let me remove this side note from here, and now we are ready to write out the rule. So then log base b to the n x is going to be equal to 1 over n log base b x. So again, with the set of restrictions in the first line here, we ensured that there is not 1 in the base of this log, and there is also not 1 in the base of this log, so we ensure that neither of these logs have got a base of 1. Now, let's move on to the actual proof and see what's going on in here. Well, let's start with log b to the n x and try to think about what we can do here. We can apply the change of base rule that we looked at in the previous video, video 12, which I will also link for you. And then we can rewrite this log as a base b. So what would that mean? Remember what we need to do here. Log new base old argument over log new base old base. Okay, now the numerator will not change. That's just going to be log base b x. But what do we recognize at the denominator of this fraction? Well, if you watched video 6, then you can recognize that this is basically just equal to n. And then remembering that dividing by a number that is just basically the same as multiplying by the reciprocal of that number, I can replace this as 1 over n times log bx. So here is your rule. This was one of the easiest proofs because this rule was basically just a simple application of the change of base rule, right? Let's do some practice questions. And for those practice questions, we will need a bit more space again. First question. Log base 9, 27. Well, 27 is not a straight power of 9, so it would take us a bit of time to sort of figure out what exact power 27 is of 9. So it's simpler to recognize that 9 is 3 squared. And now, because there is an exponent in the base, I can use the rule that we've just proved, and I can replace this whole expression as 1 over 2 or a half times log base 327. In the next step, I'm going to keep the 1 over 2, but then the whole point of me starting on this journey was that I recognized that 27 is a power of 3, and that is 3 cubed. Remember, 3 times 3 times 3 gives you 27. I remember that log base 3 cubed is just equal to 3. So the whole answer is going to be 3 over 2. Now, how can I check if I am right? Well, I can check by remembering that the log is the exponent. So I need to raise 9 to the 3 over 2 power. So that's going to be equal to 27. Now, is this true? Well, remember from video 7 in the exponent series, which I will link you again, is that if we have got a fractional power, that can be rewritten as a root and a power. So I can replace this 9 to the 3 halves as square root of 9 cubed. And again, I remember that I can switch the square root and the cubed around. So this is the same as square root of 9 cubed. So square root of 9 is 3, and 3 cubed is conveniently equal to 27. So we are right. Example 2. Log base 8, 32. What is this equal to? Again, we recognize that both 32 and 8 are powers of 2, so it would make more sense to rewrite the base as 2. Now, first we recognize that in the log base, we can replace 8 by 2 cubed, and the argument of 32 stays. But now here again, we can apply the rule that we're discussing today, which is if there is an exponent in the base of the log, I can write out the exponent itself as a 1 over multiplier, and then I can keep the log base with the base of the exponent, which is 2, and the argument stays. Okay, so now I'm keeping the 1/3 and I'm keeping the log 2 base, but now I remember that 32 is 2 to the 5. And again, just like in the previous example, this can be replaced by just the exponent. So the whole expression is going to cancel down to 1/3 times 5. And remember, when you multiply a fraction with a whole number, you just multiply the numerator. So that's going to be 5 over 3 as the final answer. If you wanted to check whether this is the correct answer, I suggest you go through the same manipulations I've done in example 1, but to make sure the video is short and concise, I'm just going to move on to the next example now. Make a bit more space. Example 3. I have got log b squared 3x squared. Now, the problem here is that I don't know the exact base and I don't know the exact argument. So my solution is not going to be a nice neat number like a half or a third. But still, I can make this log a little bit simpler by applying these exponents in the log base rule. So let's do just that. We can bring out 1 over 2 and then we can have log base b 3x squared. Now, if we wanted to, and I suggest that we do, make this argument a little bit simpler, just have single arguments. So what we can apply here is, because there's a multiplication in the argument, we can apply the multiplication behind the log rule, which was in video 7, and break these out into individual logs but addition. Not forgetting that the half is multiplying the whole log, so we need to keep that multiplier out. So that's going to be log base b 3 plus log base b x squared. Now, when looking at this expression, we notice that in the second term, the log b x squared, there is a power in the argument, so we can bring that power down. Let's keep the half out here with the bracket. So we still got log base b3, we can't really do anything with that anymore, and then plus 2 times log base bx. Now that's as simple as we can go, except for we still got a bracket, so let's multiply that bracket out. So I have got half log b3 plus, remember, half times 2, that's going to cancel down to 1. So in the second term, I'm just going to keep log bx. Now, you can argue that this isn't simpler because now we have got an addition and a half multiplier. But I would argue that having something squared in the base of the log is a bit more confusing, in a sense that if you have to assume that these are all economical concepts and you sort of try to feel for how they change over time, I would argue that making those decisions will be much simpler by looking at this expression. Let's look at example number 4. So I've got log x cubed in the base and 4th root of x to the 5th. Okay, so what can we do here? Now again, use the rule of today's video. Because there is an exponent in the base, x cubed itself. So bring out the power, which is 3 in this case, as a multiplier of 1 over, and then change the log base to just the original base of the exponent, which in this case is x. I'm going to do one more thing, and I remember that the roots can be rewritten as fractional powers, so I'm going to replace the argument as x to the 5 over 4 power. Why did I do that? Because in this case now I can just simplify the log x to the 5 over 4 to 5 over 4, because now I have got the argument as a power of the base of the log. So 1/3 times 5 over 4. And that's going to be equal to 5 over 12. Remember, when you multiply a fraction with a fraction, you multiply the numerator by the numerator and the denominator by the denominator. So 1 times 5, the top numbers give me 5, and 3 times 4, the bottom numbers give me 12. And I cannot simplify it any further because 5 can only be divided by 1 and 5, but 12 cannot be divided by 5. Would you have imagined that this complicated looking original expression is virtually just 5 over 12 in disguise? Logs are quite interesting in my opinion. I hope you share that view. Last example for the video, and I think I'm going to make a little bit more space to ensure we don't run out just in the middle of the example. So log y to the fifth x to the 2/3 times 5y cubed. So again, we have got an exponent in the base of the log, so we can rewrite that as 1 over 5 log base y x 2/3 5y cubed. Now again, just like in example 3, we're going to apply the multiplication behind the log sign rule and break these out into individual logs, but keeping the 1 over 5 multiplier. So the first term will be log y x 2/3 plus log y 5 plus log y cubed. Okay, so let's move further. I'm going to have to keep the 1 over 5 multiplier because that's multiplied the original log. So it has to multiply every single one of the new terms. And then I see that there are exponents in the argument of both terms, the first and the last. So those can come out as multipliers in front of the log expression. So the first term is now going to be 2/3 log base yx plus log base y 5 plus 3 times log base y. But log base y is just 1, or I might have even spotted that log base y cubed is equal to 3 right away. So the last term is just going to be 3 on its own. But I still have to multiply out the bracket. So I have 1/5 times 2/3, that's going to give me 2/15 times log base yx plus 1 over 5 or 1/5 times log base y5 plus 1 over 5 1/5 times 3 is just going to give me 3 over 5. Now, arguably, this result is not as simple as the previous examples when we just ended up with one single number, 5 over 12, but still, it has got a simpler, potentially more understandable expression because now we just have got y and x. Well, that was the 5 examples for today, and that was how we prove the rule when there is an exponent in the base of the logarithm. So, in the next video, we're going to look at the 9th rule in our list, and that is when we have got different base logs that all cancel down to 1 at the end. I hope you learned something in this video, and I hope that you'll join me next time. Thank you for watching. Bye.